Picture the first second of the universe as a blinding fireworks show where every spark has a perfect shadow spark, matter and antimatter, racing toward each other to cancel out. And when they touch, they don't fight. They erase into pure light. If that balance was truly perfect, you and I aren't here. No atoms. No stars. Just a bright, empty afterglow. So what interrupted perfection? By the tiniest imaginable margin, and turned. Nothing should be left. Into everything you've ever loved? I'm Rowan K. Mercer, and this is the Science Audit. Today we're not chasing trivia. We're stress testing the story we tell ourselves about reality. Because symmetry, the idea that nature doesn't play favorites, sounds like the kind of principle the universe should be built on. It's elegant. It's clean. It's almost moral. And yet this simple symmetrical prediction is brutal. Matter plus antimatter should have annihilated back into light until nothing with mass remained. But look around. We live in a universe made of matter. Galaxies, planets, lungs drawing breath, hands building telescopes, brains inventing equations. Existence is the leftover. And the universe seems biased, barely, and we don't fully know why. So here's the promise of this audit. We're going to make antimatter feel real, not abstract. We'll build the naive symmetrical expectation. Why? Everything should vanish, is the default conclusion. Then we'll bring in what we've actually measured, what the standard model of particle physics can and can't explain, and why that remaining gap is one of the cleanest hints that our model of reality is incomplete. Now come with me mentally to a moment so early that space is not a calm stage but a churning ocean of energy. The universe is hot enough that mass is cheap. It's a factory running at full capacity. Out of the heat, particles appear. Antiparticles appear. They meet. They annihilate. They reappear. It's like trying to count individual droplets inside a waterfall. And yet somewhere in that chaos, a tiny accounting error becomes the Milky Way. Let's make sure the foundation is rock solid. Antimatter is not science fiction. It's not negative matter. It's matter's mirror twin in the quantum sense, same mass, opposite charge, and some other flipped quantum labels. The electron's antimatter partner is the positron, same mass, but positive charge. The proton's partner is the antiproton. Put the right set together, and you get antihydrogen, an antiproton with a positron orbiting it. Not an idea, an object we have built and held, briefly, in laboratory traps. And when matter meets antimatter, the universe performs one of its cleanest tricks, conversion. The mass becomes energy, typically in the form of high-energy photons, gamma rays. If you want a metaphor, think of matter and antimatter as two perfectly matched bank transactions, a deposit and a withdrawal of the same amount. When they meet, the ledger goes back to zero and all that remains is a receipt printed in light. That receipt can fly across the universe. This isn't optional behavior. It's not a special case. Annihilation is what you expect when a particle encounters its antiparticle. Which means that in a universe that begins by making both in huge numbers, the default ending, if nothing else happens, is mutual erasure. So why doesn't our sky scream, antimatter, at us? Why isn't the cosmos a patchwork of matter galaxies and antimatter galaxies colliding at the boundaries, lighting up the universe with telltale gamma-ray glow? We'll get there. But first we have to name the kind of matter that dominates the question. Most of what you and I are made of is built from baryons. That word sounds technical, so let's translate it. A baryon is a heavy, composite particle, like a proton or a neutron, made of three quarks bound tightly together. If atoms are architecture, baryons are the bricks. Now here's the astonishing observational fact. There are far more baryons than antibaryons in the observable universe. And the imbalance is not a little. In human terms, it's cosmic, but it's also weirdly tiny as a fraction. The most common way to say it is this: for roughly every billion pairs of baryon and antibaryon the early universe produced, there was about one extra baryon left over. 1 in a billion. Picture a stadium filled with a billion couples who all pair off and exit together, except for one single person left standing. That lone survivor doesn't just go home. That lone survivor becomes every star, every planet, every ocean, every cell. This is the first point I want you to actually feel, not just understand. Everything you've ever touched is built from the residue of an almost perfect cancellation. You are made of the universe's leftover margin. So the audit question becomes sharper. What kind of laws allow a near-perfect symmetry to break in a consistent direction? What mechanism produces a tiny bias, then locks it in so it doesn't wash away as the universe keeps expanding and cooling? Physicists have a way of framing this that I love because it's both coldly logical and strangely intimate: the Sakharov conditions. Named after Andrei Sakharov, they're essentially the universe's checklist for making more matter than antimatter. You don't need all the math to feel why they matter. Condition 1, you need a way to break. Baryon number. Think of baryon number as a bookkeeping rule, an accounting label that says how many baryons exist minus how many antibaryons exist. If that number can never change, you can shuffle particles around forever and never create a net surplus. It would be like trying to end the day with more money while forbidding any new income or loans. Impossible. So the universe must have some process, at least in the early high-energy era, that violates that accounting rule. Condition 2, you need the laws to treat matter and antimatter differently in some subtle way. Here we step into the language of symmetry, and I'll translate as we go. C. Symmetry means charge conjugation, swap particles with antiparticles. P. Symmetry means parity, take the universe and reflect it like a mirror. CP symmetry means do both at once, swap matter with antimatter and mirror the spatial coordinates. If CP were perfectly obeyed, the universe would not prefer matter over antimatter. Their behaviors would be perfect reflections. But CP symmetry is not perfect. We have measured CP violation, meaning the laws have a tiny twist, a preference that leaks in. The first cracks were seen in the 1960s in particles called kaons, and later in exquisite detail with B mesons. These are unstable particles that exist for fractions of a second, and yet in their decays, the universe reveals a microscopic favoritism. Matter decays one way, antimatter decays a slightly different way. Not dramatically, not loudly, but measurably. Condition 3, you need the universe out of thermal equilibrium. That phrase can sound like a textbook trap, so here's the lived version. In equilibrium, every process that makes something is balanced by a reverse process that unmakes it at the same rate. It's like standing in a crowded train station where for every person walking in, another walks out. You can't build up a crowd if the flows perfectly cancel. To lock in a matter surplus, you need a one-way door moment, a period where expansion and cooling change the rules fast enough that the bias freezes in, before the reverse reactions can erase it. Those are the requirements. They're not a theory by themselves, they're a filter. They tell us what any successful explanation must contain, no matter how beautiful the details are. So where do we stand right now? We've confirmed antimatter exists. We create it. We use it. Positrons are used in PET scans in medicine, positron emission tomography, where antimatter helps doctors see metabolism inside the living body. In particle accelerators, antimatter appears routinely as energy turns into particle-antiparticle pairs. At CERN, physicists have assembled antihydrogen and trapped it long enough to test its properties. Antimatter is not hypothetical. And yet the cosmos, on the largest scales we can observe, looks like a matter kingdom. We see galaxies made of matter. We see interstellar gas made of matter. The cosmic microwave background, the afterglow of the early universe, carries the imprint of a universe that evolved with a small but decisive matter surplus. So you might think, okay, we have CP violation measured in the Standard Model, the reigning theory of particles and forces. Doesn't that solve it? Doesn't that tiny favoritism add up over cosmic time? Here's where the model starts to strain. The Standard Model does contain CP violation, but when we run the numbers under reasonable assumptions, it appears too small to explain the observed matter surplus. That sentence looks modest. It isn't. It's a crack in our most successful description of fundamental physics. Because the matter surplus isn't a minor detail, it's the precondition for chemistry, for stars, for any observer to ask the question. Symmetry predicts nothing should be left. And yet here we are, living in what should have been an empty receipt of light. Now, I want to take you back, imaginatively, into the early universe as the temperature falls, because this is where the story becomes visceral. Picture the universe cooling through thresholds like water freezing into ice. Except instead of water molecules, the ingredients are quantum fields, the invisible substances that particles are ripples of. As the universe cools, it undergoes transitions, like phases of matter, where the rules of what exists and how it behaves shift. One of the key transitions is the electroweak phase transition, when the electromagnetic force and the weak nuclear force become distinct as the Higgs field takes on a non-zero value everywhere. If that sounds abstract, hold this metaphor. The Higgs field is like a cosmic medium that gives certain particles their inertia, the way moving through water feels different than moving through air. Early on, that medium behaves differently. Later, It settles into the state we live with now. And here comes our first candidate explanation. Electroweak baryogenesis. The name is a mouthful, but the idea is cinematic. If the electroweak transition in the early universe was violent enough, like bubbles of a new phase nucleating and expanding, then at the moving bubble walls, processes could occur that favor matter over antimatter, generating a surplus of baryons. It's like a freezing front moving through a lake. The boundary between liquid and solid can trap impurities, leaving one side slightly different from the other. In the cosmic version, the impurity is a tiny CP-violating bias that gets trapped as the universe changes state. The appeal is huge. It uses known physics near energies we can, in principle, probe. It ties the origin of matter to the Higgs mechanism, which we've directly confirmed by discovering the Higgs boson. It feels like the universe making matter during a moment of upheaval, dramatic, plausible, testable. But here's the issue. In the standard model as it stands, that phase transition doesn't appear to be violent enough. It's more like a smooth crossover than a first-order bubble boiling event. And the available CP violation still looks too feeble. So electroweak baryogenesis almost works, and almost is where new physics loves to hide. It suggests we may need an expanded Higgs sector, extra Higgs-like particles, or other additions that change the early universe dynamics and increase CP violation. People talk about supersymmetry-like ideas or other beyond standard model frameworks. Not because theorists enjoy complexity, but because the universe is presenting us with a bill, and our current model can't quite pay it. Now the second family of explanations takes a different route, one that feels almost like a clever legal maneuver in the universe's accounting system. Leptogenesis. Instead of trying to directly create a baryon surplus, you first create an imbalance in leptons. Leptons are a different family of particles: electrons, muons, taus, and most mysteriously, neutrinos. Neutrinos are like ghost notes in the cosmic symphony. They pass through you by the trillions each second, barely interacting, carrying information from the deep interior of stars and from the early universe. The leptogenesis idea says, what if the universe first tilted toward leptons over anti-leptons, and later, through known electroweak processes, part of that lepton imbalance got converted into a baryon imbalance? In other words, the universe might have cheated, creating the matter surplus indirectly. This is elegant for a reason that should make you pause. Neutrinos already hint that the standard model is incomplete. We know neutrinos have mass, but in the simplest form of the standard model, they shouldn't. That means there is already a door open to new physics in the neutrino sector. Leptogenesis often involves heavy neutrinos, much heavier than anything we can currently produce, existing in the early universe. Their decays could violate CP symmetry and generate the initial lepton asymmetry. The tragedy, scientifically, is that this is hard to test directly. Those heavy particles may be far beyond our accelerators. But the beauty is that the consequences might leak into things we can measure: neutrino properties, rare processes, patterns of CP violation among leptons. So if electroweak baryogenesis is the universe making matter in a dramatic phase change storm, leptogenesis is the universe making matter through a quiet, almost bureaucratic rerouting of imbalance from one category to another. Different aesthetics. Same goal: explain why anything with mass survived. Now the third family of explanations is less about one specific cosmic event and more about the possibility that our current equations are missing a hidden tilt. New sources of CP violation. If the laws of physics contain additional CP violating phases, extra tiny twists, then the early universe could have amplified them into the matter surplus we see. Here's the metaphor I want you to carry. CP violation is like a microscopic phase angle in the universe's choreography. Imagine an orchestra playing a piece that should be perfectly reversible. Play it forward, play it backward, it's the same. CP violation is a subtle timing offset in one instrument section. Tiny. Almost unhearable. But if the piece repeats enough times and interacts with a changing environment, that offset can decide whether the whole symphony drifts left or right. A tiny twist in equations becomes the Milky Way. So how do we hunt for that hidden tilt? One of the sharpest tools is the search for an electric dipole moment, an EDM, of fundamental particles like the neutron or the electron. An electric dipole moment is basically a separation of positive and negative charge within a particle, like a tiny internal compass needle for electric fields. If a neutron had an EDM, it would mean its internal charge distribution is slightly lopsided along its spin axis. Why does that matter for CP violation? Because a permanent EDM in a fundamental particle is a smoking gun for new CP violating physics beyond what the standard model comfortably provides. EDM experiments are astonishing. Tabletop scale apparatus, ultra-controlled environments, absurdly precise measurements of how spins process in electric and magnetic fields. And yet what they are really doing is reaching back toward the birth conditions of the universe, asking, was there a deeper asymmetry written into the laws? This is one of my favorite moments in all of science. The early universe feels unreachably grand, and then you realize someone can probe its secrets with a device smaller than a room. Now, at this point, a natural question rises, because the mind wants the simplest escape hatch. What if antimatter isn't missing? What if it's just far away, hidden in pockets we haven't seen? It's a fair instinct. Maybe there are antimatter galaxies, antimatter clusters, vast regions of the cosmos made of anti-stars. If so, there would be boundaries where matter and antimatter meet. And at those borders, annihilation wouldn't be subtle. It would generate gamma rays with characteristic energies, a kind of cosmic warning flare. We look for that. We have gamma ray telescopes. We map high-energy skies. And so far, the observations strongly constrain the idea of large nearby antimatter domains. That doesn't mean you can mathematically rule out every exotic configuration at every distance, but it does mean the maybe half the universe is antimatter and it's just over there story is not supported by what the sky is telling us. Another question people ask, quietly, and sometimes sensationally, is whether antimatter falls up. Does it respond to gravity differently? Here's the careful, honest answer. All evidence so far points to antimatter having the same gravitational behavior as matter. General relativity treats energy and mass as the source of gravity, and antimatter has positive energy. But the only fully satisfying way to settle this is to measure it directly with neutral antimatter systems like antihydrogen, because charged antimatter is dominated by electromagnetic forces that swamp gravity. Those measurements are happening. Antihydrogen is trapped, cooled, and released to see how it accelerates in Earth's gravitational field. The results to date are consistent with antimatter falling down, not up, within uncertainties, and the precision continues to improve. This is not a loophole that likely solves the matter-antimatter asymmetry, but it is part of the audit. When you're testing the completeness of reality's rulebook, you check every assumption. So where are we, emotionally and intellectually, right now? We're standing at the edge of a paradox with a ledger in our hands. On one side, the Standard Model, a triumph of prediction, confirmed by particle experiments again and again. It contains CP violation. It contains processes that can, in principle, violate baryon number through non-trivial electroweak dynamics. It's not naive. On the other side, the observable universe, which insists that matter won by about 1 part in a billion, and that win was decisive. Not a rounding error, an existential one. If the Standard Model's CP violation is insufficient, and many analyses suggest it is, then new physics isn't a luxury. It's demanded by the fact that you exist to notice anything at all. Let's do a thought experiment together, a reality model stress test. Imagine we discover tomorrow a new CP-violating process. Something clean. Something unambiguous. A new particle interaction that tilts the early universe more strongly toward matter. On the surface, it would make existence feel less miraculous. We would have a mechanism. A story with gears. But at a deeper level, it would do something stranger. It would tell us the universe is not built on perfect symmetry as a default. It would tell us that asymmetry, this tiny, lawful unfairness, is part of the bedrock. The cosmos would not just be balanced and elegant. It would be selectively biased in exactly the way required for structure. And that forces a philosophical reframing that is grounded in measurement, not poetry. The ancient question, why is there something rather than nothing, stops being purely metaphysical. It becomes partly empirical. Because nothing should be left is a prediction you can derive from symmetry, and something is left is a fact you can observe. The gap between the two is where new knowledge lives. Now bring it down to the human scale, because if this stays cosmic, it stays distant. You are a pattern of atoms that had no right to survive under naive symmetry. The carbon in your muscles, the calcium in your bones, the iron that lets your blood carry oxygen, none of it forms in a universe that annihilates into photons. Every inhale you take is a vote cast by the leftover baryons that shouldn't have been there. And here's a detail that always gets me, even after years in physics. The early universe didn't need a huge bias. It didn't need a dramatic victory. It only needed a whisper of preference, 1 extra baryon per billion pairs, and then the cooling cosmos did the rest. Expansion diluted the plasma. Reactions froze out. Annihilation ran until it couldn't find partners anymore. And that tiny residue became the raw material for all complexity. So when you hear 1 part in a billion, Don't hear small. Hear total. Hear everything. Because in the annihilation era, the universe burned away almost all of its mass into light, and then the surviving 1 in a billion fraction became the entire cast of the cosmic story. Now let's step back and audit what we actually know, versus what we want to be true. We know antimatter is real. We know the early universe produced matter and antimatter abundantly. We know annihilation is efficient. We know there is a baryon asymmetry, measured in multiple ways, consistent across cosmology and particle physics. We know CP violation exists. We know the universe was out of equilibrium in its early expansion history. Those are the pillars. What we don't know is which mechanism, or combination of mechanisms, actually generated the observed surplus. Was it tied to the electroweak transition with new Higgs-related physics? Was it seated in the neutrino sector through leptogenesis? Are there undiscovered CP-violating phases waiting to show themselves in EDM experiments or rare decays? Or is it something even more alien, something we haven't named yet because we haven't seen the first clue? That uncertainty isn't a failure. It's a map edge. And this particular edge is special because it's one of the rare points where particle accelerators, precision tabletop experiments, and telescopes all converge on the same existential discrepancy. A detector that fits in a lab can speak to the first instance of time. I want to slow down for one more moment, because it's easy to forget what the alternative would have looked like. If matter and antimatter had annihilated perfectly, the universe would still be something, in a technical sense. It would be filled with photons, light cooling as space expands. It would be beautiful, bright, a cosmic sea of radiation, and empty. No atoms to bind, no chemistry to awaken, no long-lived stars to forge heavy elements, no planets, no eyes to see the light. Just the afterglow, fading forever. So when you see lights, street lights in winter fog, candles on a quiet night, the cold blue of a phone screen illuminating a human face, let that be a reminder of the original light the universe almost became. The fact that we have structure, instead of only illumination, is the gift of a tiny asymmetry. Now this synthesis, what have we learned on this walk to the edge? We started with a simple, brutal symmetry argument. If the early universe made equal matter and antimatter, annihilation should leave essentially nothing with mass behind. But the universe we observe is matter-dominated, with a surplus of about 1 baryon per billion antiparticle pairs. The standard model contains CP violation, but likely not enough to explain that surplus. So the remaining gap isn't a footnote, it's a signpost pointing beyond our current laws, toward new physics that could be hiding in high-energy transitions, neutrino properties, or ultra-precise symmetry tests like EDM searches. Here's a contemplative takeaway, a thought experiment to carry into your own life. Imagine you could rewind the universe and rerun the opening minute 1 trillion times, each run with the same laws but different quantum outcomes. Would matter win every time? Would it win half the time? Or is the bias so deeply written into the rules that the universe almost can't help but leave survivors? And if your very existence depends on a tiny asymmetry, what does that say about the way we think of balance as a virtue of reality? And now the next great question, the door we haven't opened yet. If the universe needed symmetry to break in order to produce matter, what other features of our reality, time's arrow, the growth of complexity, even the stability of memory, might also be consequences of tiny, lawful imperfections? If you want to keep going, click the video on the end screen. I picked it because it continues this same audit of reality from a different angle, and it will make this mystery feel even sharper. And I want to hear from you. What do you think is the most plausible culprit? New CP violation, neutrinos, or something we haven't imagined yet? Answer with just one phrase. If you subscribe, do it for a specific reason. This channel is building a library of rigorous, human-scale explanations of frontier physics, so when the next clue drops from a lab or a telescope, you'll already have the framework to understand what it changes. If symmetry is nature's default, then you are the evidence that the universe learned how to break it.